Hi, I'm Alistair, and this is an electronic escape room puzzle that uses these arcade push buttons. Now, there's lots of different puzzles you can make using button inputs. You can make a puzzle where players have to press the buttons in the correct order. And they might be shown that sequence as in a Simon game, or they might have to derive it from trial and error or logical deduction. Either way, they've got to remember and repeat a particular pattern of inputs. Or you could make a puzzle that tests players' reactions, where they have to press buttons quickly as they light up, like in Whack-A-Mole. Or you could create a coordination puzzle, where the buttons are located somewhere separate from the instructions that describe how and when they must be pressed, so that two or more players have to share information and direct each other to activate them in the correct order or at the correct time. Now, in this puzzle, I've tried to incorporate lots of those elements all together. So, to open the door, players simply need to get all of these buttons lit up at the same time. Now, imagine that the buttons are physically distributed around the room. They might be out in the open, they might only be discovered after opening a box or gaining access to another area. Or they might be visible but just out of reach, so that players need to use some sort of long tool to push them. And when you press and hold them down, the buttons light up. So if you have a sufficiently large team of players, all they need to do is position themselves correctly and then coordinate themselves to press all the buttons down simultaneously. Then when they do that, the door opens. Easy. But what if there's more buttons than there are players? Now in that case, they're going to have to be a bit smarter. And what they might realise is that the buttons actually stay lit for a short time after they're released. So if they're quick, a single player could press one button and then, while it's still lit, activate another one. But there's another trick, because not each button stays lit for the same duration. This yellow button stays lit for half a second, and this red one here goes off almost immediately. But the blue one over here, well, that stays on for 2 seconds. So if a single player has to activate both of these two buttons, they need to work out that it's much easier to hit the blue one first, and then they've got more time to get over to the red one than if they attempted to do it the other way round. So this is not a complicated puzzle, but it does involve observation, reasoning, dexterity, communication, and coordination. And in the rest of this video, I'm going to explain how you can build this puzzle yourself. So let me talk you through the hardware I'm using. Now, obviously this is only a scale model of a door, but despite its small size, it's otherwise perfectly formed. So there's a 12-volt maglock here with its armature installed on the inside of the door. And there's also a spring here, so that when all of the buttons are pressed and the maglock releases, the door springs open. Now, the power to the maglock comes from this barrel connector here, which is connected to the load side of a relay. So we've got a 12-volt power source coming in, connected to the common terminal of the relay. And when the relay is toggled, that common terminal switches between normally closed or normally open terminals, which in turn makes or breaks a circuit between the power source and the output to the maglock. Now, the thing that causes the relay to toggle is the control signal that's sent from the Arduino here. So this is a 5-volt relay module, so it's connected to 5-volt, to ground, and then the signal line is wired through to GPIO pin A5 on the Arduino. Now, there's a couple of other bits of hardware here that I want to mention. The first is these grey blocks here. These are Wago connectors, and they're really easy ways to join wires together. They have these levers that you can just lift up and then push a wire into that terminal and just click it down again. And these terminals are then all connected together. So you can get 4-way, 5-way, 8-way connectors. And the reason I'm using them here is to create a common shared ground. So all of the arcade buttons have a wire from one side of their microswitch connected into this block here, and then I connect that block through to one of the Arduino ground pins here. So all of the arcade buttons are connected through to Arduino ground. And the other side of the switches comes in here and is connected to pins A0 to A3. And I do the same on this side for the LEDs. So the anodes of the LEDs are connected separately to pins 2 to 5, while the cathodes are all wired to ground, shared between this Wago block. Now the Arduino itself is mounted on a screw shield, and that again is really just a convenient way to manage connections. I know a lot of people are a little nervous about soldering components, but you really can't rely on just pushing wires into a breadboard for a permanent solution either. So a screw shield is a good alternative. It gives you a robust connection, but you can still undo and reconnect any components as required. Now, with both the connections to the Wago blocks and to the screw shield, you might notice that the wires have got these small white ferrules crimped onto the end of them. Now, not everyone uses these, but they are generally considered best practice. So I'm using stranded cable, which means it's nice and flexible, unlike solid core cable. But when you connect the end of a stranded cable into a terminal like this, you want to make sure that the strands of wire don't fray or splay apart and accidentally cause a short circuit. So that's why I've placed one of these ferrules onto the end of them. So let me show you how to use them. First of all, strip off about 1 centimetre of insulation from the end of the wire, and then I just twist the strands together. Then select a ferrule. They're colour-coded by size, so here I'll use a white one, which matches the 22 AWG wire I'm using. Then you take a crimping tool like this, place it over the end, and then just squeeze it to crimp the ferrule onto the wire. Now sometimes you might need to repeat that just a few times, and then you should have a nice, solid, secure connection and no frayed strands. And here's a wiring diagram just to illustrate those connections. We've got the buttons at the top with one side of their micro switches going to pins A0 to A3 and the other to this shared ground via that Wago connector. And then these are the LEDs that go inside the corresponding buttons, which also have a shared ground to that Wago connector, and then they are connected to one of the GPIO pins between 2 and 5. Now, because I'm lighting up these LEDs from the 5-volt output from an Arduino, I replaced the resistors they came with, which were designed for a 12-volt arcade game, and I put in these 220 ohm resistors instead. Now, I've made another video recently all about these buttons, so please take a look at that if you need any more information about them. And then at the bottom here, I've got the relay module, which is switching this 12-volt power supply to the maglock on the door. Now let's take a look at the game logic, which is running on the Arduino. So here it is. Notice that I'm not including any additional libraries. Everything is contained solely within this one script, and it's only about 50 lines long. So this is a very nice, compact code project. We start by declaring some constants which describe how the hardware is configured. So I'm using 4 buttons in this example, and those buttons have got their switches wired to the following GPIO pins, and then the LEDs for each button are wired to these GPIO pins. I've then got one more GPIO pin which is wired to the signal line that controls the relay module. Now there's nothing special about any of these particular pins, so you can use whatever available pins you want. You can increase the number of buttons as much as you want, so long as you have available GPIO pins on your microprocessor. Then we get onto the global section, and the global section has got 3 arrays in it. All of them have one element for each button we're using. So the first array is the button duration, and this states the time in milliseconds that each button will stay lit for after it is released. So I've got 100 milliseconds, half a second, 1.2 seconds, and 2 seconds. The next array, this is the last press time, and this is the timestamp at which each button was last pressed. So microprocessors, all of the Arduino style and ESP style microprocessors, keep track of the number of milliseconds that have elapsed since they were first powered on. And we're going to use that to compare it to the timestamp when a button was last pressed to determine whether this duration has elapsed or not. Now, to know whether in any given frame the button is active or not, we'll record that in this final array that we've called button active. This is an array of Boolean values that's simply true or false as to whether it's currently lit or not. Okay, we go into the setup function, and the setup function is very straightforward. We initialize a serial connection, although we don't actually ever make use of that in the code. I only do that because out of habit I always initialize a serial connection and I output the name of the file and the date that the code was last compiled, just so that when I find this Arduino lying around and I plug it into my computer, it will spit out what code it's running, which I find very useful just to keep track of all my projects. But we're not actually making use of the serial connection anywhere else in the code. Then what we need to do is we just loop over all of the buttons. Each one has an input, which is coming from the micro switch into the button pin, and it has an output, which is going from the LED pin into the LED that's in the button housing. We initialize the relay pin that's connected to the relay that energizes the maglock, and we initially write a high value to that. I'm using an active low relay, which is the most common type I see available, so we'll drive that signal pin low when we want to release the maglock and open the door. And then we go on to the loop function. So the loop function is the main body of the program that simply repeats over and over for as long as it is powered up. And the first thing we do is we grab a reference to that millis function I mentioned. So this is the number of milliseconds for which the code has been running for. And we will assign that to a variable which we'll call now. That means that we are able to make use of that value in a couple of tests further down the code in a moment. We'll then also create a Boolean flag variable which we'll call allActive, and that will set to true when all of the buttons have been pressed at the same time. Now we'll give it an initial value of true because what we'll do is we'll assume that's the default state. Our kind of null hypothesis will be that all the buttons have been pressed, and then we will simply disprove that if when we go to look at each button in order we find out that they haven't been pressed. So we give it a default value of true, but that might change to false in a moment. Then what we do is we actually loop over all of the buttons in turn, and we look at them one at a time, starting with the 0th button where I is equal to 0, and we test whether that button has been pressed at the moment. If it is being pressed, then when we take a digital reading of the corresponding button pin, we'll return a low value because the buttons were wired up to be connected through to ground when they're pressed, and that means that a digital reading will give us a low value. If that's the case, then we will assign the value in the last press time array corresponding to the button index that we're looking at the moment to the current timestamp, which we got from the now variable here. So remember this array at the top here, which started off as all zeros, and this was the timestamp at which each of the buttons was last pressed. Supposing the code has been running for 2.5 seconds now, and we're going through the loop after 2.5 seconds, if the first button is being pressed at that point, we will update the value of the first element in the last press time array, so this, to 2500, for example, because that's 2.5 seconds after it's been running. All right. And then what we'll do is we will use that value that we've just assigned in the last press time array in some further tests down here. So the next thing we're going to do is to work out, based on the value in the last press time array, is this button currently active or not? And that depends on what the time is now and also how long this button lasts for. So we compare the difference between the current timestamp and the timestamp at which the button was last pressed. And if that is less than the length of time that the button stays active for, then we know that the button is currently active. So we'll assign the ith element in the button active array based on the result of this test. Whether this statement is true or false, we'll set button active to be true or false. And then, having created this variable, we'll then use that to decide whether to light the LED up or not for this button. So we'll write a value to the ith LED pin corresponding to either true or false, depending on whether that button is currently active or not. So in a simpler version of this code, let's say where the LED was lit up for as long as the button was pressed and then released immediately afterwards, what you'd have to do is simply digital read the button pin and then digital write the LED pin based on that value. But ours is a little bit more complicated here because we've got a level of indirection between them. When the button pin is pressed, what we're setting is the last press time, and then we're calculating whether the button is active or not based on comparing the last press time to the current time, and then we're using that to write the LED pin high or low to turn the LED off or not. Okay, so that's what's going on here. And then finally, this is the test which I mentioned here about the all active flag. So we initially said that we're going to assume that all the buttons are active, but if any one of them is not active, as we loop through this loop here that goes over every button one at a time, if we encounter any single one of them not active, that means that we can set the all active flag to false, because we know that at least one of them has failed the test. And it doesn't matter whether all of the other ones are active or not. As soon as we've encountered one that isn't, we can set that to be false. And then the final line of the code here, having now derived this value here from the button active test, we write the relay pin either a high or a low value, depending on whether the buttons have all been activated or not. If they've all been activated, we'll write a low value that will switch the relay contacts over, break the connection to the maglock and open the door. However, if any one of them has not been activated, then all active is false, and in that case we will write a high value instead. And that's the last line of the code. That really is it. So there's not very much to it at all. And in the loop section here, I hope you'll be able to follow how we're kind of incrementally deriving each of these values from the last. The first thing we do is we see whether the button is pressed. That updates the last press time. Then we use the last press time and the button duration to determine if it's active. And then we use an active button to determine whether to write the LED pins. And then we use the active button of any individual button to set the all active flag. And then we use that to activate the relay. So it's kind of fairly sequential logic, and hopefully that all makes sense. So that just about brings me to the end of this video. I hope you enjoyed it. I like this project because it tests quite a range of players' skills. It requires observation, reasoning and deduction and reactions, and by varying the number of buttons, where they're positioned relative to each other, and the duration for which each one stays lit, you can adjust the relative importance of each of those elements. This is also a great example of a puzzle that you can adjust the difficulty by simply changing that duration. And you could do this in advance based on the number of players in the game, or you could do it in real time to make an adaptive difficulty puzzle that gets easier as more incorrect attempts are made. Now, As always, I will upload the Arduino code which I demonstrated along with the wiring diagram and any other additional resources onto my Patreon account, and I'll put a link to that in the description below. If you'd like to access those or any of the resources for any of the escape room projects which I've shown on this channel, please do head over there and check it out. And I want to say thank you very much to all my Patreon supporters who enable me to create these projects every month. I really appreciate your support. Thank you. Otherwise, if you have any questions or comments or suggestions, do please let me know and I'll try to get back to you. And I just want to say thank you very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.